Good morning, everyone. My name is Andy Gavel, and I'm a professor here at the Howard University School of Law. On behalf of Dean Danielle Holly Walker, my faculty colleagues, and our students, I'd like to welcome the FTC and all of you to Howard for hearing number 7 of the FTC's hearings on competition and consumer protection in the 21st century. We are very happy to co-sponsor today's event, and I want to thank the FTC and the many people at the agency and here at Howard who have worked hard over the past few months to organize these hearings. As you all know, today's topic is algorithms, artificial intelligence, and predictive analytics. As is immediately evident from both the list of questions the FTC has posed and the agenda for today and tomorrow's programs, these hearings have been purposefully designed to take a broader and more interdisciplinary perspective than any of the previous ones. Moving well beyond the usual collection of academic and practicing economists and lawyers, FTC staff have assembled an impressive collection of academics, public servants, technologists, scientists, engineers, and industry leaders. But of course, there's still lots of lawyers and economists. The goal is to educate the agencies and the broader competition and consumer protection policy community so we can all obtain a better understanding of the technologies that are transforming our economy as well as our political and social environs. We will hopefully learn more so we can better understand the business models and practices of our time, and so we can differentiate myth from reality, promise from near and long-term prospect. The ability to take on this kind of perspective study is a hallmark of the FTC and one of its great institutional strengths. It is especially fitting that such a forward-looking approach is being taken here at Howard. Only 2 years after Howard University was chartered by Congress in 1867, this law school was founded, with the aspiration of producing lawyers who would lead the future fight to realize the full promise of the Reconstruction Amendments to the Constitution of the United States. Next year, we will celebrate our sesquicentennial, and for that occasion, instead of looking backward, we have selected a theme that looks forward, the next 150. As is true for the FTC and for today's hearings, any institution that fails to look forward is bound to fall backward. In closing, please note that the event is being photographed and webcast and will be posted on the FTC's website, and that by participating, all attendees consent to those conditions. Please also note that our students will be coming and going throughout the day and are available to answer your questions. Please get to know them while you are here and feel free to seek them out if you have any questions or concerns. And finally, it's my great pleasure to introduce our first presenter. Our scheduled presenter, Michael Kearns, has been slightly delayed, so we're going to start with John Dickerson from the University of Maryland, and hopefully Michael will arrive in time to follow John. Again, welcome, thank you, and enjoy the hearings.
Good to go.
Goldman. I'm an attorney in the Office of Policy Planning at the Federal Trade Commission, and I just want to introduce you to John Dickerson, who is an assistant professor in the Department of Computer Science at the University of Maryland, College Park. Welcome.
Thank you, Karen. It's a pleasure to be here. I am John Dickerson. I'm a, third-year assistant professor at the University of Maryland and right up the street in College Park. And today I'll be talking about an introduction, briefly introducing the audience to algorithms, AI, and predictive analytics. And so for this talk, I'd like to start with a motivational quote, which sounds like it was written a long time ago, and that's because it was. So although machines can perform certain things as well or perhaps better than any of us can, they infallibly fall short in others, by which means we may deduce that they did not act from knowledge, but only from the disposition of their organs. And this sounds old because it was written a long time ago. It was written by Descartes, who was a philosopher and mathematician in the 1600s. So quite a long time ago, folks were already thinking about what does it mean to think? Can we mechanize thought? Another famous philosopher from the 1600s, Hobbes, states reasoning is nothing but reckoning. So reckoning here is just a reference to mathematics. So reasoning is nothing but mathematics, essentially. And so some time passed, 1600s, 1700s, 1800s, until the 1900s, when some breakthroughs occurred in logic and mathematics and philosophy. Folks like Boole, folks like Hilbert, made some breakthroughs in the formalizations of mathematical reasoning. So recall, we think reasoning is nothing but reckoning, and now we can reckon, perhaps, with mathematics. So there were some proofs showing that some hard limits, there are some hard limits to what mathematical reasoning can do. But subject to those limits, folks like Alan Turing came around, Church came around and said there are certain machines, simple machines, that for any of these mathematical reasoning problems, subject to these limits, we can create a machine that can do this. So this is nice. This builds on now hundreds of years of philosophy and mathematics. But the general pitch here is that if intelligence can be simulated by mathematical reasoning, that is, reasoning is just reckoning, and mathematical reasoning can be simulated by a machine, then can a machine simulate intelligence? So AI, artificial intelligence, the word was coined by John McCarthy in either 1955 or 1956, depending on how you count. It's 55 in a proposal to fund the Dartmouth Summer Research Project on artificial intelligence. And you'll hear this called the Dartmouth Conference. This occurred in the summer of 1956. And there are some fun quotes in there saying basically we can solve artificial intelligence in 3 months or we can solve artificial intelligence in 1 generation. But the one I'd like to pull out is that every aspect of learning or any other feature of intelligence can be so precisely described that a machine can be made to simulate it. So even in the 1950s, 1960s, folks were making statements like this. So a quick spoiler, this hasn't happened yet. We can just shut this down right now. But progress has been made. So how does that progress occur? Well, this is a cycle of basically R&D progress that you'll see repeating in the AI world, and this has happened since basically 1956, where some new advance, maybe a new technique, new hardware, happens. Fast progress is then made on old hard problems. So it could be a new mathematical technique, it could be new hardware. GPUs, these graphics processing units, are one of the main drivers in the current sort of fast progress being made on old hard problems that we're seeing now. But eventually, you start to hit roadblocks. And at this point, the academic community, the industrial community starts to get pessimistic. This bleeds into the press. And at that point, everyone is pessimistic about progress, funding dries up, progress dries up, and so on. We wait until the next large advance. And so this is a cycle that occurs in most sort of verticals. It occurs in AI research as well. In AI, though, we call it a cycle of basically AI summers and AI winters. The winters are when funding dries up and nothing happens. The summers are basically what we're going through right now, where we're seeing large advances driven by sort of recent hardware and mathematical advances. So this is a bit pessimistic, this cycle, but like I said, progress has been made. So this has been cycling for arguably maybe 6 or 7 times since the 1950s, but every time we go through this loop, progress is made. New problems are solved and new problems are encountered. So what is AI? AI, many definitions, the one I'll use here, is the ability to process and act based on information via automation. So we can break this down roughly into 4 segments. One is perception. I want to be able to perceive the world around me. That could be the physical world, that could be the virtual world. I want to be able to learn something about it. So I get some signals about the world, then I learn something about it. Maybe I learn a model. I want to abstract and generalize that model so that I can use it in other situations. And what do I mean by use? Well, maybe I can reason about this information, I can reason using my model, and then act within the world. Again, that could be virtual, that could be physical. So if I can create this automated system, roughly, I have created what we would call AI. So let's keep moving through this history of AI until we are where we are today. Roughly, we can split AI research into some first wave AI, second wave AI, and then maybe 2.5 or third wave, which is where we are right now. In this first wave, primarily, researchers focused on what is called search. So this is either searching through a potential solution space. Some quick examples. Chess is a good example here, where we had, say, Deep Blue beating Kasparov via a sophisticated algorithm that did search through using domain-specific heuristics, expert knowledge, for instance. Folks who played a lot of chess encoded heuristics into the search algorithm. It would search through the solution space to find, say, the next move to play. Now, another hallmark of first-wave AI is something called expert systems. And this also relies on basically bringing in a lot of expert knowledge to form some sort of large database of rules, of knowledge, of facts about the world, using some sort of inference engine, typically based on logical reasoning, to make new sort of conclusions based on these facts, and then some sort of action I/O system to interact with the human. So this is basically the world up until maybe the 80s in terms of AI. Now, there were some large successes here. So one example that I used earlier is this chess champion falling to basically a sophisticated search algorithm. And there are many more. And in fact, techniques from first-wave AI are still used in practice. But they're decidedly brittle, and they really don't have any real learning capability. So they're really sort of a function of just the knowledge that you encode into them. There's a huge overhead to encoding that knowledge. Right? I have to ask, say, every member of the audience and everyone watching to tell me all the facts that they know about the world, and then I have to store that somehow. And that might be brittle, that might not be generalizable. They're very, very brittle systems, but they do allow me to do in-depth specific reasoning. Right? If I ask a bunch of experts for facts on a specific vertical, then I can do a lot of fast automated reasoning about just that vertical. So that can be good, but it's very difficult to generalize. And if you recall back to that earlier slide, we want generalizability, we want abstraction, because we want to create some system that's able to encounter new environments and still act in a reasonable way. So, in terms of those 4 boxes, first-wave AI generally does perception reasonably well, in the sense that I've asked all audience members to give me facts, and it can do reasoning and acting reasonably well, but it won't learn and it won't generalize. Now, there were some transition points in multiple areas of sort of AI research. One of these is something called natural language processing, which says, can I get a computer to ingest, say, raw text? Or can I get Alexa to ingest signal from your voice and then have it understand that in some sense? So in natural language processing, up until about the late 1980s, most of the rules for doing this sort of translation or understanding were done via hard-coded sort of expert rules. Around the late 80s, probabilistic models started to come into play. Okay, so this is going to sound more like machine learning, like folks have maybe heard about in the press. These are models that ingest, in this case, large text corpora and learn patterns in that data. To look at a different vertical in AI, so autonomous vehicles rely heavily on something called computational vision, which says, hey, I have a video image. Can I understand what's going on in that image? Say I'm a car and I'm driving along and I have a still image of the road in front of me. Can I understand that there's a stop sign and a pedestrian and a dog in front of me and so on? So in autonomous vehicles, in the mid-2000s, DARPA ran what they call a grand challenge. In fact, their first grand challenge, which asks, can I create a vehicle that can drive some 100+ miles across the desert autonomously? In 2004, no vehicles completed this task. In fact, I think the longest trip that a vehicle took was something like 10 miles. And these vehicles relied heavily on hand-coded rules that say something like, in general, when you're 10 degrees away from the sun and you're driving forward at a particular speed, then a shadow is going to be a shadow instead of a rock with some set of features associated with it. And again, this is a very brittle system. This is not going to generalize very well. But then in 2005, 5 teams completed the entire trip, so 100+ miles. And this is because they started using these probabilistic models. And in fact, you can see the general manager for the program, Strat, at the time, had a fun quote. Vehicles were scared of their own shadows, hallucinating obstacles when they weren't there. And this is for those prior systems. And then probabilistic models allowed them to get around this. So you can see similar transition points throughout all core AI areas in the late 80s, in the 90s, up and through basically the mid-2000s. And this happened because of three things. One is computational power increased. And this is the story of basically computation since the 40s or 50s. This has played a driving role in AI development as well. Number two, storage costs decrease. I don't have to pay a lot of money to store a lot of data. And three, everyone in this world now relies on statistical models. Maybe with some expert input, but still statistical models. So this takes us into the second wave of AI. And there's no hard date for this because it happened differently in different verticals in this world. Here, we're relying on this assumption now that we've learned the hard way multiple times that encoding all knowledge explicitly does not work. It doesn't scale. It's very brittle, and it's very difficult to handle uncertainty. The new idea is that we should create a general statistical model for a problem domain. We should create a statistical model for natural language, or for a type of natural language, or for autonomous driving, a type of autonomous driving. What do we do with that model? Well, we feed in data from the real world, or maybe simulated data, until it looks right. And this is going to be characterized by statistical learning. So the reason why these models have taken off is because if we input a different data set, or say set of data sets, into these models, we'll learn a different model, and then we can deploy that in a different environment. So it's much more generalizable. Now, some examples. In machine translation, for instance, going back to this natural language that we discussed earlier, we can feed in multilingual text corpora to learn relationships between language. So say we want to translate French to English. One of the early multilingual text corpora came from Canada, where there are rules stating that, say, any government ruling has to appear both in English and French. And so now we have a mapping between English and French documents. We can feed that into a model, and we can learn a way to translate between the two systems. Autonomous vehicles. We can feed in videos and tests of successful driving into a model, and then learn what scenarios are safe or not safe, or maybe put some error bars around what scenarios are safe in general. Face detection, face recognition. I can feed in many labeled faces of people. Here is where the face is, or here is where the face is and an ID associated with that, to learn what a face looks like, or to learn what, say, your face looks like. So these types of models are very good at perception, and they're very good at learning. Remember, we're training these models, these general models, based on a data set, and if we feed in a different data set, we're going to get a different result. So they're reasonably good at abstraction and generalization as well, so long as your model is general enough, and so long as you have enough data. But there is no reasoning or acting. I've made no statements about, say, when one should turn the car in the turn the wheel in the autonomous vehicle. So a quick example model. Remember, these are systems that rely on statistical learning to train probabilistic models that will tell us something about the world. A quick example is a neural network. So these appear a lot in the news now, which is why I've chosen them. But they're not a new idea. Indeed, that 1955 proposal where McCarthy defined AI, used the term AI for the first time, also discusses neural networks. I believe they were called neuron networks at the time. So this is not a new idea. The general idea of neural networks is that one should pass information into this input layer, which you see on the left side of the screen. So that information could be pixels of an image. That information could be something with audio signal. It will cascade through the network along basically a series of pipes that go through nodes. And these pipes have, say, different widths that can be controlled by a learning algorithm. And then the final layer of this network that has information flowing through it will create some sort of guess. In the case of, say, classifying images, here we have cats and dogs. It's going to create, say, a probabilistic model of whether or not an image is a cat or a dog. And that gives you some signal as to how good or bad your statistical model, in this case a neural network, is acting. A very general model, so long as we can feed information into it via that input layer, and so long as we can judge the output, and so long as we can actually learn, so make the network better using sophisticated optimization techniques, we can use this for many problems. And indeed, that is what we've seen. So long as we can, again, train these models through repetitive sort of optimization algorithms. So another sort of buzzword that one sees in the press a lot is a deep neural network. Again, not a new idea. These existed, I think, since the 1980s. And they're just these neural networks that we had on the last slide, but with more quote-unquote hidden layers. These are the layers in between that input and that output. So I can add more and more of these. I can create more piping, intricate piping between these different nodes to learn new patterns in the data. And sometimes, indeed, we can stack many, 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 many more nodes, so order of hundreds of thousands, millions, et cetera. So these are very large models. And again, this is because we have increased computational power and cheap storage. That idea for deep networks has existed since the 80s, but we've seen them taking off in the last 5 to 10 years because of advances in hardware, because of a huge increase in the amount of data that exists. So we have large firms collecting data, we have the government collecting data, and we can now store it cheaply, access it quickly. And because, indeed, from the R&D community, there have been much better methods developed for learning basically how to make a good one of these. They're hugely successful. They're good at detecting anomalies in data, for instance, credit card fraud. They're good at voice recognition. You've seen Alexa, Siri, Google Assistant, et cetera. They're great at machine translation, language generation, game playing, some recent high-profile success stories such as AlphaGo playing basically expert level Go, Deep Stack playing expert level heads-up poker. Self-driving cars are starting to take off. Video search, audio search, finance, et cetera. These are all success stories in part due to deep learning. Not a new idea, driven by advances in hardware and training, though. Nobody understands why they work very well. And this is a common story in AI as well, and this is something that we're seeing more and more appearing, which is humans have sat down, they've designed the network structure, they've designed what those nodes and what those connections between the nodes look like. Maybe they're encoding some domain expertise. There are some known heuristics that you can rely on. There's a trial and error process, and maybe actually other AI is actually coming in and trying to train these models or structure these models in a better way. But nobody knows when or why they don't work in general. So they work well in expectation, which is why we see machine translation systems, which is why we see Alexa and Siri in households now. But when they fail, it can be very confusing, it can be reasonably catastrophic, and it can be very hard to explain. And some recent research pushes, funded by the DoD, funded by industry, funded by nonprofits, have started noticing that, hey, an adversary can exploit this kind of behavior. When I have a system I trust most of the time, but it can be exploited in very odd ways, and I don't understand why or when that happens, then I can wreak some havoc in these systems. So I'd like to take a step back. So now we've talked about deep learning, we've talked about machine learning, we've talked about AI. And roughly, AI is this sort of four-pillar approach to perceiving the world, learning about it, building an abstract and general model, and then using that to act and reason. Machine learning is just one way to build these models, where we do not focus on acting and reasoning, but we focus on perception, on learning, on abstraction, and on generalization. And deep learning is just a specific form of basically representational learning, so it's a type of machine learning. Okay, so every time you hear deep learning in the news, you can replace it with machine learning mentally. It's just a way to solve a machine learning problem. So some present-day movements in AI, understanding bias and methods for debiasing. You'll hear about this, I think, throughout today and tomorrow, many of the topics on this slide. So this is sort of a teaser. Understanding bias and methods for debiasing. So if I feed skewed training data into these systems, remember these are statistical models that are trained on data from somewhere in the world. If I feed skewed data into the system, then I'm going to learn something that represents that skewed data. So how do we understand when that happens? And can we create systems that still feed in this biased data, which might be the only data that exists, but spits out a model that is debiased? As mentioned before, adversarial reasoning in multi-agent systems, learning to act with cooperative actors, learning to act with adversarial actors. So bringing in older fields such as game theory into these new methods for solving those problems. How do I, say, design, well, I'll talk about this in a few slides, but how do I design policies as a firm to compete with other, say, firms that are both cooperative and adversarial? Can I do this based on machine learning? Also mentioned on the previous slide, robustness to noise, robustness to adversarial attacks, both in terms of theoretical robustness and empirical robustness. How do I design automated systems that fail less, that are robust to attacks, and that fail more predictably? Because obviously these systems will always fail at some point. And in that vein, explainable AI, there's a lot of money going into this as well, because it's very difficult to interpret the results that come out of these systems from time to time. So can we produce human understandable models that also work well? And one final move in the AI community has been reinforcement learning. It's a type of machine learning, but it's a type of machine learning that also focuses on learning to act and reason. So now we're getting closer to that initial definition of artificial intelligence. Here we have an agent, maybe physical, maybe virtual, that's going to act within an environment. It's going to receive a reward signal and then maximize total reward. It wants to find the actions to take for any state in the world, such that when it takes that action, it is treated well in the future. It receives reward and expectation in the future. And I'll give you some examples of this at the end of the talk. So here again, reinforcement learning, not a new idea. But deep networks have been used extensively here to revolutionize their use in practice. So here we have deep networks that are used to, say, reduce the complexity of representing the environment. Remember, I can't actually write everything down. I don't want to represent every single fact in my computer. So now I'm going to learn some abstraction of the world and then act on that. So reinforcement learning is taking us closer to what we want to call AI. We have perception, we have learning. These are just like machine learning. We have abstraction and generalization, again, moving toward that. Again, if we train these models on different data, we get a different trained model. And we're starting to move toward reasoning and acting here. So in the context of this audience, I thought I would do maybe a quick deep dive into a few uses of AI, particularly in something called market design. So markets provide agents the opportunity to gain from trade. Many markets require structure to operate efficiently. Market design is going to tackle this problem via what's called economic engineering. So I put on my economist hat, and I put on my engineer's hat, and I put on my mathematician's hat. I'm wearing 3 hats at this point, but I can use these hats to design a market. How do I structure the market? How do I constrain the market such that I achieve some sort of efficiency goals? AI is increasingly helping with the design of these markets. For instance, these automated methods can use data to help designers characterize families of market structures. They can be used, obviously, for predictive methods that anticipate, say, future supply and demand in electricity markets or finance markets. One example, as a computer scientist, this is close to my heart because a lot of the money in our world comes from this, is using AI in online advertising. So online advertising markets generally match advertisers with consumers. Many billions of dollars, and this is an increasing market, many, many billions of dollars are being used here, and it's a driving force in the technology sector. Machine learning models in this space right now are being used to divide customers into very fine-grained and automatically generated segments. So no longer just male, female, but something far, far more fine-grained than that. That's learned automatically. They're being used to set reserve prices in auctions based on user modeling and bidder behavior. Again, automatically. They're being used to automatically generate the creatives, that is the artwork that you see pop up on your screen, automatically generate those, say without human input, to fit a specific customer's predicted wants. All automated. Reinforcement learning based tools, remember this is that form of machine learning that also focuses a bit on acting, are being used to help advertisers, for instance, bid automatically on these very fine-grained segments. Remember now we have, say, millions of segments. How do I bid on that? I can use a machine learning-based model to do this. Another example, AI in electricity markets. Here, matching supply and demand is extremely important. It relies heavily on demand forecasting. Machine learning-based techniques are going to provide very accurate demand forecasting, which leads to very stable market prices and more efficient power usage. Reinforcement learning-based techniques, remember ML plus some form of acting, are going to allow us to activate or deactivate expensive, heterogeneous power sources to maintain that stability. So I can predict better demand. I can predict better demand at particular time points further into the future, and then I can make a plan to boot up or boot down particular power sources such that I maintain market stability, such that I reduce brownouts, and so on. Again, automated. And my final example is AI and kidney allocation. This is close to my heart. I've done a lot of work in this space. So here, kidney exchanges, for instance, are an organized market where patients with end-stage renal disease enter and are able to swap donors, willing living donors, to receive new organs. It's a really interesting paradigm that's been around for, say, 15 years now, and it accounts for something like 10, 11, 12, 13% now of all US living donations of kidneys. Hundreds of transplant centers are involved in this organized market, in fact, multiple organized markets. And here, AI-based tools are also operating. Now, this isn't fully automated, but they are, for instance, semi-automatically and optimally, subject to human value judgments, matching donors to patients, both in the US and also worldwide. Here I've called out the United Kingdom and the Netherlands, but in many countries. They're providing sensitivity analysis at a level that humans cannot for new policies. And they're learning from data the quality of, say, potential matches in this market. Now, let's return to some open questions and some recent pushes, which will, I guess, trigger good discussion for the rest of today and tomorrow. So one is, how and why does deep learning work? So I've mentioned not a new idea. Neural networks existed since the 50s. Deep learning existed since the 80s. Now we have new hardware. Now we have new training techniques. These tend to work very well in expectation, but when they fail confusingly. Why do they work? How can we handle incentives of competing agents? All those three market examples that I showed you, firms are obviously going to compete against each other in this space. The government, regulatory agencies have their own incentives as well. Individual participants have their own incentives. How do we handle this? How do we encode other aspects, such as fairness, accountability, and transparency into these systems? How do I ensure that my automated system doesn't marginalize, say, an already marginalized class in the ever sort of increasing hunt for efficiency? How do I even define this? How do I define fairness? This is a classic question in economics that computer scientists are now starting to struggle with as well. How do I implement this in a scalable way, in an understandable way? Ethical AI, this will be talked about, I believe, later by folks like Henry Kautz. How do I divide the labor between policymakers, such as those in this audience, who are ethically trained and ethically minded, and technically trained, perhaps ethically neutral, AI and machine learning experts? So I can implement, say, a very sophisticated system, but I need to then produce some sort of aggregate output that I can pass back to policymakers to ensure that this is reflecting the aggregate human value judgments of those who control the systems. How do I do that? And there are close ties in this sort of exploration to the world of privacy and the world of social norms. So in general, our end goal is to create these systems that perceive the world, learn from it, create some sort of generalizable model, and then inevitably learn to act using that model. We're not quite there yet, but there's a lot of hope in this space. But I'm going to say that maybe this isn't even the biggest problem. The biggest problem is going to be the interplay between these systems and society, ethical issues, societal norms, human value judgments. How do we play between, say, these sort of sophisticated machine learning-based approaches to what I've shown here on this slide and the rest of the real world? So I'll leave it at that.
Thank you very much. Excellent introduction and for the questions that will be coming throughout this hearing.
Do I need to mic up, or am I all good this way?
So, as I mentioned, I'm Karen Goldman. I'm with the Office of Policy Planning at the FTC, and now I'd like to introduce our next speaker, Michael Kearns, who is a professor at the Department of Computer and Information Science at the University of Pennsylvania. Welcome, and we're looking forward to your address.
Okay, thank you. So not only am I late, but I also missed the deadline to give slides last week. So there's 2 strikes against me already. But hopefully the time I would have spent hacking PowerPoint, I put into thinking instead. And so I'm just going to speak informally from notes. So as she said, I'm on the computer science faculty at the University of Pennsylvania. My main research area is machine learning and related areas. I've been in this area since I was a doctoral student in the 1980s, before machine learning was a thing in society. And so I was just asked to give some introductory framing remarks based on the agenda that I saw. which contains like lots of topics that are near and dear to my technical and related interests. In particular, following on the last speaker, in the last few years, I've been thinking quite a bit about ethical and social issues in the use of machine learning and algorithmic decision making more generally. And I also saw that there's some discussion or a panel about sort of competition and marketplace questions introduced by machine learning. I hope to make some less technical remarks about that because I think there's less scientific to say there, but a lot of interesting things to discuss. And also relatedly, topics related to consumer protection and abuses by machine learning and AI. And so what I just want to do with my time is make some informal remarks, provide some personal opinions on these topics based on my own experiences and research, and you know, hopefully cue things up for the next couple of days for the rest of the speakers. As the last speaker mentioned, there's been a lot of discussion, really not first in the technical community, but first in the mainstream media and society at large, about the many things that can go wrong when applying machine learning and AI and related methods to algorithmic decision making. And before I describe, let's say a little bit more about what can go wrong and what we might hope to do about it scientifically, I thought I'd start by sort of just framing how things can go wrong in the first place. And so one thing you might wonder is, you know, if there's a lending model or consumer credit scoring model that exhibits racial bias, for instance, or there's some data analysis or machine learning methodology that leaks personal private consumer data, you know, you might, it's a reasonable thing to wonder whether this happens through active malfeasance. You know, are there evil programmers at tech companies who, you know, put in a line in their code that says if the person's race is this, then do this, if it's some other race, then do something else, or whether they program backdoors into their code that permit privacy leaks. And there's good news and bad news here. My strong belief, and I think those of people who work in the field would say that no, there's absolutely no such malfeasance going on by evil programmers at technology and other companies. So that's the good news. The bad news is that the truth might actually be a little bit worse, which is these sort of collateral damage or consequences are actually the natural byproduct of applying, you know, the formal fundamental scientific principles of machine learning and AI, and I'll say a little bit more about that. The vast majority of what I think we would call algorithmic decision making is actually a little bit more specifically almost always driven by machine learning these days. So in particular, when you think about the algorithms that make things like lending decisions or decide what ads to show you on Facebook or Google, these generally are not what you should think of as hand-coded or programmed algorithms, but rather they're the result of taking data, you know, historical data, whatever that might mean in a given domain, giving it to an algorithm, and that algorithm, of course, trains a model on the data, and then at the end of the day, it's the model that's actually making the decisions. It's the model that's actually deployed in the field. And typically, the algorithm that transforms the data into a model is actually tremendously simple and very principled from a scientific standpoint. So if I had slides, one thing I like to do in forums like this is put up the Wikipedia pseudocode for the so-called backpropagation algorithm for neural networks, which the previous speaker mentioned. And that pseudocode is literally a simple loop with about 10 lines of code in it. And a real working version of it wouldn't be that much more complicated. And it's doing the most obvious thing you can possibly imagine, which is essentially going through the training data and adjusting the parameters or knobs of the model in order to minimize some, you know, usually accuracy or error-based cost function, okay? So that algorithm is not opaque at all. It's entirely transparent. Sometimes, you know, when I talk to people who aren't in the field, they naturally assume that machine learning algorithms, you know, the code for them might look like something like I imagine the code to a video game like Grand Theft Auto looking, you know, hundreds of thousands of lines of spaghetti code with all these special cases and details, and it's not like that. So then the natural question to ask next is, you know, if the complexity doesn't lie in the algorithms themselves, then where does the complexity creep in? And of course, it's from the interaction of the data being processed to produce a model mediated by these very, very simple algorithms, okay? And so the problems arise these days not so much from the algorithms themselves, which again are very simple and operating on very basic well-motivated scientific principles. The problem is really when you work in extremely large, complicated model spaces, of which deep learning is just one and perhaps the most recent example. The sort of space of models has a lot of sharp corners in it, as I might put it, which allow you to kind of optimize the thing that you're trying to optimize, like minimizing the error on the data, at the expense of other things that you didn't explicitly ask for, like fairness or privacy. And I think if there's one kind of important adage to understand about machine learning, it's that basically modern machine learning will not give you for free anything that you don't ask for and specify. And in general, you shouldn't expect it to avoid things that you don't want, that you didn't tell it you didn't want. Okay? And this is, I think, the source of a lot of the kind of violations of social norms and values that we've seen by machine learning and AI in recent years. So that's a little bit about what can go wrong. Now let me talk a little bit about, that's a little bit about how things can go wrong. And sort of with that background, I want to talk about, well, what are the different things that can go wrong? And most importantly, what can we do about them from a kind of scientific standpoint? So, the things that can go wrong are things that I've mentioned already, which is violations of things like privacy or fairness or interpretability and transparency or even safety or morality, if you like. The sort of logical extreme of this, for those of you who have heard of it, is this sort of parlor game or science fiction thought experiment known as the singularity, in which AI, AI achieves superhuman intelligence to the point that, for lack of a better term, the robots become our overlords. While that's a fun thing to think about, I don't know many sane people in the machine learning community who actually think that that's our sort of gravest technological risk anytime soon. All you need to do is kind of see what AI and machine learning can actually achieve right now and compare it to humans or other biological species, and you will be deeply underwhelmed by what we can accomplish so far. But violations of social norms are like already with us now today, and on a very large scale, whether we know it or not, or whether we're measuring them properly or not. I think it's important to say to this audience that I think I and many of my colleagues, we do believe that better laws and better regulations are possible and should be developed, and I'm sure that that's being worked on and is a necessary activity. But I think my opinion is that will be woefully inefficient in the algorithmic era to actually keep up with the types of violations of social values that we're seeing, because basically human organizations don't scale, and you can't sort of expect to police the sort of violations I'm talking about with sort of regulatory agencies that are poring over the decisions made by algorithms on sort of a human timescale and hope to keep up. So an alternative approach, which I'm a great advocate of, and as are a growing number of people who do technical work in these areas, is to design better behaved algorithms in the first place, and to actually endogenize various notions of social norms inside of our algorithms, and asking that our algorithms, that the actual code obey some definition of privacy, some definition of fairness, some definition of morality, if you like. And of course, this leads immediately to two very difficult questions. The first difficult question is, how do you define these things, as the last speaker said? How do you define algorithmic fairness? How do you define algorithmic privacy? And then if and when you can come up with such a definition, it's going to come at some cost, right? So if I have some notion of fairness in models that are used to provide criminal sentencing guidelines, my asking for fairness from that model by gender or race will come at a cost of accuracy. What I'm saying is like a tautology. If I ask myself to find the model in some space of models which minimizes the error, period, and then I ask to find the model that minimizes the error subject to your favorite definition of fairness, the error can only get worse. And so in a model like, let's say, in a setting like criminal sentencing, this means that a cost to accuracy might mean sort of, hard things to think about. It might mean incarcerating more innocent people, or it might mean letting more guilty people go free. So there will be societal and technical costs to imposing these sorts of constraints on our algorithms. But I think my view and the view of many people in the field is that we have to go down this road. We have to design algorithms that incorporate these values. We have to talk about what the possible definitions for these values are. And we need to study these trade-offs between the thing that people normally optimize for in machine learning, which is accuracy, and the trade-offs to different social norms. Okay, and so what I want to do with most of my remaining time is just tell you a little bit about the sort of very active research that's going on in the computer science and machine learning and related communities on this scientific agenda, sort of picking definitions for different social values or norms and actually encoding those norms inside of our algorithms and then trying to study what the trade-offs will be with things like accuracy and other more standard objectives. So let me first talk about sort of the work that goes on in the area of privacy in machine learning, and not just in machine learning, but more generally in kind of data analysis and data science. And I think it's helpful to say just a little bit about the distinction between what I'm thinking of as privacy and a closely related and complementary area, which is that of security and cryptography. So security and cryptography, to a first approximation, is a technology about keeping data locked down. It's about controlling access to data and making sure that people who shouldn't have access to data don't get that access by basically hacking into a system that they shouldn't hack into. And this is largely the domain of security and cryptography. And that's one notion of privacy. That's sort of control of your data and making sure it doesn't get accessed or stolen by people who shouldn't. Here I'm talking about something a little bit different and more nuanced, but in many ways is equally as pervasive and important as notions of security, which is the fact that you have all this data that's being collected by different companies and agencies and other organizations, and you might worry about what not just sort of who's accessing that data, but what can be inferred about you from that data that isn't directly in the data itself. So the kind of thing that I'm concerned about here is that if your medical record is used as part of a study to build a predictive model, let's say, for some disease based on symptoms, and then that model is published or used in the field, could it be that the use of that model or the publication of that model, perhaps combined with other publicly available data sets, actually reveals a great deal about your own personal medical status and record? Okay, and if you go down the road of thinking about possible technical definitions of this type of privacy, I believe that most of you would eventually come to two kind of, I think, important conclusions or desiderata from any sort of privacy definition for machine learning or data science. One is that you need to account for the fact that any particular data set that you want to keep private in some technical sense will not be the only data set in the world. And in particular, that data set might be combined with other data sets that you don't know about or didn't foresee or don't even exist yet but might exist in the future. And one consequence of this that I will state without proof is that this means that any definition of privacy that involves anonymization is essentially a flawed definition of privacy, right? Because anonymization refers to taking the data set that's in front of you and doing things like eradicating personally identifiable information. But the literature and news is, rife with examples where you anonymized one data set, somebody else anonymized a second data set, those two data sets were combined and then maybe combined with some publicly available information, and your specific data could be backed out of that. You could be, as we like to say, re-identified, or the data set could be de-anonymized, as they say. And I think many people feel strongly enough about this assertion that there's sort of a saying in the field which is, anonymized data isn't. meaning that whatever you think you did to de-identify individual identity in a data set, that can often be undone through the unforeseen combination of that data set with other data sets. The other, I think, sort of axiom for any definition of privacy that's important is that in order to have a definition of privacy that still allows us to do anything useful with data, it's important to isolate the potential harm that comes to somebody as the result of the use of their data in some analysis or model building exercise versus the harm that might come to them just because data analysis reveals some facts about the world. So for instance, if you were a smoker in the early 1950s before there was discovered a link between smoking and lung cancer, well, when somebody did data analysis and discovered that there was a strong correlation between lung cancer and smoking, and you were a smoker, that fact does harm to you, but it doesn't matter whether your data was used in that analysis or not, right? Researchers were going to discover this fact whether your particular data was used or not, and a harm was done to you by the fact that suddenly it's revealed that smoking is bad for your health and you are a smoker and everybody knows it. But that harm was not done to you specifically as a result of the data analysis using your data or not. You were basically, this harm was going to be done to you whether your particular medical record went into those studies or not. And so there's a very rich definition of data privacy known as differential privacy that was introduced about 15 years ago and has received a great deal of scientific attention in the interim, and now has a very rich theory and a very rich body of algorithms that basically, on the one hand, meet this sort of very strong notion of data privacy, which has to foresee the possibility of triangulation through the combination of multiple data sets on the one hand, but still permits sort of powerful use of data. And so, one kind of pseudo theorem that I will state to you is that everything that we pretty much know how to do today in machine learning, we also know how to do in a differentially private way, and it's just a matter of companies adopting this technology and choosing to do their machine learning and data analysis in a differentially private way. And we're actually starting to see large-scale deployments. Both Google and Apple use differential privacy in meaningful large-scale ways in some of their services, and maybe more importantly, the 2020 US Census, every single statistic or report that they release as the result of the 2020 census, they are planning to do so under the constraint of differential privacy. And so this is an example, I think, of a very promising kind of case study, right? Of course, people have thought about different definitions of privacy and data analysis and machine learning for a long time. There was a struggle to kind of come up with the right definition. Many of us believe that sort of definitions based on anonymization are fundamentally flawed, but then a better definition came along around 15 years ago. There's been a huge amount of research on this particular definition, and the good news is that for this particular definition of privacy and this particular social norm, it is possible to sort of give these very powerful guarantees at not too great a cost to accuracy or computational efficiency and the like. We can sort of, have the best of both worlds, if you like. So let me say a few words about research in fairness in machine learning and algorithmic decision making, which is much more recent. It's a much more nascent field than the study of privacy in machine learning and AI. But we already know a fair amount about it, and one of the things we already know about it is that it's going to be a little bit messier than privacy. So my claim is that if you waded into these literatures and you looked at the work that's gone on in differential privacy and looked in particular at the definition of differential privacy, you perhaps, like many people, might sort of agree that this is sort of the right definition of privacy. So we already know that there's not going to be a right definition of fairness in algorithmic decision making and machine learning. And what do I mean by we know there's not going to be a right definition? So there's already, from the last several years, several examples, several papers which have results of the following form. They basically say, well, whatever your definition of fairness is, wouldn't we all agree you'd want it to have at least the following 3 properties? And you kind of look at those 3 properties and you say, yes, yes, I would definitely want any definition of fairness to at least meet those 3 properties, and probably other stuff too. And then, of course, the punchline of these papers is, well, guess what? Here's a theorem proving to you that you cannot simultaneously achieve all 3 of those properties in any definition of fairness. Okay, so those of you that have a kind of economics or social choice background might know about like Arrow's impossibility theorems for sort of voting systems. These have a very similar flavor. And so this has very concrete consequences. So in particular, a typical notion of fairness in machine learning would ask for the approximate equality of false positive or false negative rates across different groups. So let me give an example. Suppose you're a mortgage company and you're trying to build a statistical model that tries to predict from people's loan applications and credit history whether they will repay a loan if you give it to them or not. Okay? Very natural thing to want to do. And you want this model so that when people apply, you can make a prediction about whether they'll repay or not, and then you want to give loans to people that will repay you and not give loans to people that you predict won't repay you. But because this is a statistical model, you're going to make mistakes. You're going to have both false positives and false negatives, right? And we might think of false negatives as really the case that causes harm to the consumer in question, right? False negative being somebody who's creditworthy would have repaid the loan if you didn't give it to them, but you decided to reject them, okay? So we might think of false negatives as a harm inflicted on a consumer, and false positives are sort of the people that got lucky. So a typical definition of fairness would basically say that, look, you're going to make false rejections. We're not going to try to prevent that. But across different racial groups, it cannot be the case that the false rejections rate differ wildly. It cannot be the case that the rate at which you falsely reject qualified African American applicants is 3 times the rate at which you falsely reject qualified white applicants. Okay, so this is a very natural constraint. And these impossibility theorems basically say if you ask for that and you also ask for equality of false positives, i.e. the people got lucky, and one other related condition, you cannot simultaneously achieve all of these. So what this means is that we already know that in fairness we're going to have to simultaneously entertain multiple competing definitions of fairness. And so not only will there be sort of trade-offs in competition between fairness and accuracy, there's even going to be competition between different notions of fairness. If you optimize for one notion of fairness or constrain for one notion of fairness, you might be damaging or losing on another notion of fairness, okay? But nevertheless, we know this and we have to proceed anyway, and so there's been a great deal of research in the last several years on algorithmic fairness and on different notions of fairness and what the trade-offs between that particular notion of fairness and accuracy is. And this is an area where, to again echo something the previous speaker said, when you sort of talk about the potential interfaces between technical people and policymakers and other stakeholders, I think there are very, very good starting points. So one thing you can do, for instance, is if you pick a particular definition of fairness, like approximate equality of false rejections in a lending application, and you have a data set in front of you, a historical data set of people who did and didn't repay loans, you can actually trace out empirically. I would have shown this slide if I'd met the deadline. I can actually show you an empirical trade-off where on the x-axis would be the predictive error of your model. On the y-axis would be a numerical measure of the extent to which you violated this fairness notion. So 5% would mean, sort of 5% unfairness means that, let's say, between African Americans and other races, there's as much as a 5% disparity in the false rejection rates. And I can just trace out a curve for you that shows you the menu of choices you have. So you can get the lowest error, but if you sort of ignore fairness entirely, that'll give you the lowest error, but it'll give you the worst unfairness. At the other extreme, I can demand that the false rejection rates differ by 0% across populations. It's a very strong constraint. And I will get the worst error, but the most fairness, and in between you'll get something in between. And I think this is the type of, sort of quantification of the tensions that we face as a society in making these kinds of decisions, that's the right, at least initial interface between, people like me and people like you, for lack of a better term, right? Because it sort of really shows starkly the choices that you have available. Just to say a little bit more about fairness, most definitions of fairness, like the ones I've been discussing, actually only hold at the group or aggregate level. So you're only making promises to sort of groups of people in a statistical sense, and you're not making promises to individuals. So, sort of more prosaically, if you are, if you're a person of a particular race that was falsely rejected for a loan, you would have repaid that loan. The consolation that you have in these types of definitions is like, well, we're also rejecting people from other races who would have repaid their loans at the same rate that we're rejecting people from your race, which is sort of cold comfort if you're somebody who was mistreated in this way. And so a lot of recent research, including some of my own, is it trying to move towards definitions of fairness and studying their algorithmic implications that try to make finer grained promises, maybe not all the way down at the individual level, but to much finer grained groups than just things like, race, top level race or gender or the like. So these are two social values, privacy and fairness, on which in relative terms we know quite a bit already scientifically, and I think we're well on the way to kind of developing both a science and an engineering of designing better algorithms and understanding what the trade-offs are between accuracy and the various definitions of the social values that we've come up with. My former grad student and colleague Jen Wortman-Vaughan is giving the keynote tomorrow, and she's done a lot of recent research on interpretability and transparency in machine learning, which is another, of course, important social norm. I think we know a lot less there so far, partly because we just haven't had as much time. But one of the problems with sort of coming up with satisfying definitions of things like transparency and interpretability is that there's fundamentally an observer in kind of the middle of such a phenomenon, right? So when you talk about interpretability, for instance, of a statistical model, you have to talk about interpretability to whom and for what reason, and in particular, the sort of numeracy of the audience you have in mind will matter greatly, right? If we're talking about interpretability to people with like a statistics training, that means one thing. If we're talking about interpretability to the average American citizen, well, the average American citizen has not been exposed to linear regression and may find it a little bit bewildering to even talk at all about an abstract mathematical mapping from loan applications to lending decisions. And so I think much of the research that needs to happen on that topic will have to have like a cognitive and behavioral element to it. You'll need to do human subject studies with the type of audience that you're interested in and ask them what they think is interpretable to them or whether you can explain models to them and the like. So I'm almost out of time, but just to sort of quickly touch on a couple of other things that I saw on the agenda. I saw that there was there was one panel title that had a very intriguing name, which was Algorithmic Collusion. And I'm not sure exactly what the context that's meant there is. But if the concern is that, we might be entering an era where algorithmic decision-making causes in some implicit or explicit kind of large-scale way collusion between different entities, whether it's on things like pricing or decision-making or the like. I definitely think this is already happening. One area in which I'm very familiar with this already is on Wall Street, where quantitative trading teams tried to build statistical models to predict the directional movement of stocks and, so to speak, beat the market. And my basic belief there is that there's a huge amount of implicit collusion going on there. And it's really because, when we all use the same or similar data sets, and when we all use the same or similar algorithms to train our models, then even if we think we're clever and independent and creative, we are going to be strongly correlated just through the data, right? If we're trying to predict the same thing and we're using similar data sets and similar methods, then no matter what else we do, everything else we'll do is a second order effect from the fact that the data itself will correlate us. And so I think that, that this is an interesting topic on which there's probably interesting scientific things to say, but I haven't thought about it yet, and I don't know of a large body of research on it. But I'm out of time, so let me stop there and let the agenda move on.
Thank you so much.
Thank you. Okay, thank you.